Assalamualaikum and good morning. So we continue our discussion today about the Euler Head. So in this topic, I will try to discuss with you to share with you about one important parameter that's called Euler Head. So the spelling is Euler, but might be you could sound it as Euler Head. So some people call it is Euler Head, but it is okay for you to call it as Euler Head. Okay. Okay, Euler is actually names of scientists that focus on this calculation. Okay. So and then the Euler head here is actually the theoretical head. Theoretical head. So head here mean the theoretical height that can be transferred by the pump. So mean the height, the theoretical height of water that can be carried by pump. Okay, that can be delivered by a pump. Okay, so to calculate the Euler head, okay, so we need to calculate the torque. Means the torque here is referred to. We know that we have a motor here. So and then the motor will rotate a shaft, and this shaft will rotate the blade. Okay, so means that when we are talking about the force, the strength of the shaft, the rotating shaft, we not use the idea of force, but we use the idea of torque. Okay, so torque is defined as the angular momentum rate, and the equation is mvr. So this is the common equation for torque in terms of angular momentum and angular speed. So and then because we are calculating solid, we are calculating liquid here, so we do not use the idea of mass. Normally, we use the idea of mass flow rate. So we have m dot here. Okay, so and then for instance, okay, I would like to say that the angular momentum rate for liquid can be calculated as mass flow rate times the tangent velocity times the radius. Okay, so and then for this, for centrifugal pump, so the equation for angular momentum for inlet can be written as m dot v1 r1, and for the outlet is m dot for mass flow rate times v2 and r2. Okay, why we take the value of v2? Because for example, we have a blade here. So why we take v2? Because as I said, the Euler head is actually calculated to find the theoretical head. So if we talk about theoretical, means that we need to use the idea of theoretical flow. Okay, because the theoretical head means we need to calculate the head without any disturbance, without any resistance. So we have the actual flow like this one, and the angular for this one, the angular velocity for this component is actually the v1. Okay, v1 or v2. Okay, that's why we use the velocity of whirl to calculate the angular momentum. So for instance, so please remember this equation. Okay, now we need to change a little bit to rearrange the equation to suit with all the parameters that we have. Okay, let's say the angular momentum rate, for example, T here. Okay, T here is m dot v2 r2 minus v1 m dot v1 r1, and then we know that the m dot is actually rho av or rho q. So because the value of m dot here is constant, so we could simplify the equation become like this one. Okay. So and then power can be defined as torque times omega, mean time rotational speed. So we substitute the value of T here with what we have here. So we could write the power like this one. So and then we could see that we have the R2, R1 here, and also the omega. Okay, and then we could replace all that value. Okay, so we know that the correlation between linear velocity and rotational velocity can be written as U equal R omega. So means that we could write R1 is equal to U1 over omega and R2 equal U2 over omega. And then what we need to do is we need to replace this value into this one. So this is the what you should do. So and then after you write that, you could simplify the power here. P is equal to rho Q V1 U2 minus V1 U1. So this is the first equation that we get from this calculation. So and then we try to develop another equation, okay, from the idea of flow rate. So we could write the power is equal to rho GQH, okay, rho GQH. So and then we could equalize these two equations. So we could have this equation and we also have this equation. So then we could equalize these two terms. So if we equalize that one, we have power is equal to rho GQH is equal to rho Q V2 U2 minus V1 U1. Okay. So and then, so this is the assumption or the idea we could calculate the value of H. Okay. If, okay, let's say this is the H. So if the H is in maximum, as I said here, the value of H must be maximum to produce a maximum power. Assume that there are no energy losses in the system. So maximum power is an ideal condition. So you need to understand this one. So it means that ideal condition means condition that do not have any losses, do not have any friction. So that is the ideal condition. So if the ideal condition can be achieved, so means that you could get the maximum power. So means that if we could get maximum power, means the value of H there, H means the capability of pump to the height of the water that can be delivered by pump. So means that if the power is maximum, means the value of H here is the theoretical height, because it is impossible for a pump operate without any friction, without any losses. Okay, as you know, pump connected with pipe and so on, and in pipe for sure there is major loss occur. Okay, that's why I said that it is impossible for us to operate a pump without any losses. Okay, because the value of H here is the ideal condition, so we change the term H, small h, with HE here. So the term HE means the Euler head. So the Euler head here is the theoretical head. So we substitute the value of HE here. Okay, we substitute the value of HE. So and then we could simplify the equation. So we could bring rho GQ to the right side here. So and then we could cancel the value of rho Q. So we could write the HE can be written as the Euler head is 1 over G V2 U2 minus V1 U1. So this is the equation of Euler head. So please remember how to derive the Euler head, because this is the most popular question in your final or your test 2. Okay, please make sure that you could derive the Euler head. So the unit for Euler head is in meter. So why we use the unit of meter? Because it shows the height of the water that can be delivered to the that can be delivered by a pump. So that is the idea of Euler Head. Okay, so Euler Head, it is an ideal head produced by the impeller in pumping system. So ideal means that there are no losses at all. So we neglect all the losses. So we calculate the energy conversion from the kinetic to the water, and then it's converted into the potential energy. So potential energy here means the height of the delivered water. Okay, so and then after we know that this is the Euler head, and then engineers will do something to make sure that we could have a good Euler head. So mean the maximum Euler head. So the maximum Euler head can be achieved if we could make this term equal to 0. Why? Because we have a minus sign here. So means that if our pump could create some things, and then we deduct with certain value, so the value of Euler head will reduce. So the best way to get the highest amount, the maximum amount of Euler head, is to make sure that this term is equal to 0. So in this term, we have V1 and we have U1. So between these two terms, we found that the value of U1 here is cannot be 0. So it cannot equal to 0. Because U1, okay, U1 is actually reflect to the impeller speed. Because it is the tangential speed relative to the impeller speed. So if U1 is equal to 0, so means that the impeller is not moving. So it is impossible to get U1 equal to 0. So what we could do is we could make sure that the V1 here, the V1 here is equal to 0. So what is the V1? So V1 is actually the turbulent velocity at the inlet. So it is found that if we could design a very good shape angle, so it could reduce the turbulence in the inlet to the 0. So means that if the turbulence is not occur at the inlet, means that the velocity of whirl at inlet, so which is V1, will be equal to 0. Okay, so this is the idea. That's why in my previous slide just now, you could see that in inlet, so the velocity triangle is written like this one. Okay, so why we could write like this one? Because when the V1 is equal to 0, the value of VF1 now will be equal to V1. Okay, I will show you this one. Okay, so let's say this is the blade. So, and then this is the actual velocity. And then we have the VR1 here. So we have the U1 here. So, and then, okay, this is the VF1, the theoretical velocity, and this is the V1. So if the V1 here is equal to 0, so means it's become smaller and smaller and smaller here. So means that this velocity is moving towards the VF1. So this velocity will go like this, become smaller, and if the velocity V1 is equal to 0, means that it will equal to VF1. So I hope you could understand the mechanism of this one. So means that if the V1 here is equal to 0, okay, so you cannot just write the velocity vector with V1 here, and we have a V1 here without anything here. So it is wrong. It is not a vector because it's not closed loop, the resultant vector. So that's wrong. So if you don't have any amount here, so means that you need this arrow is actually will go to this point, and it will have same direction and same amount of VF1. Okay, that is the idea of this statement. So please remember that why we always want V1 is equal to 0, because we want to optimize the value of Euler Head. So how to get V1 is equal to 0? So by having a good dimension, a good design of inlet blade. And normally this is achievable by engineers. So that's why in many problems for centrifugal pump, we will use the inlet velocity triangle like this one, where we assume that V1 is equal to 0, means that the velocity triangle will become like this. Okay, so please, I hope students could understand this and could draw velocity triangle and inlet with and without V1. So if the question says that the losses or turbulence in inlet is not exist, so you need to draw the velocity triangle like this one. Okay, so again, this is maybe the conclusion for what we discussed just now. So we have three types of blade. We have backward, radial, and forward. And I show you all the velocity triangle, and this is the summary of the velocity triangle. And if you could see here, okay, the velocity triangle is simplified into this triangle because we assume that V1 is equal to 0. So means that if V1 is equal to 0, V1 is now equal to VF1. Okay, now I would like to discuss about the velocity of flow or flow velocity. Okay, for flow velocity, we could calculate the flow velocity with equation. Why? Because flow velocity is actually reflected the the theoretical velocity. So means that we could calculate it by using a few common equation. Okay, the equation is we want to calculate the velocity. So it is equal to flow rate divided by the cross-sectional area. So and then in textbook we will found that the extensive equation or it can be calculated by using Q over pi dB. So Q is the flow rate of the pump, and D here is the diameter of the blade, and the B here is the width of the blade. So means that if you want to calculate VF1 at the inlet, you must use parameter at the inlet. So the equation is equal Q over pi D1 B1, and VF2 will become Q pi D2 B2. Okay, this equation actually comes from this idea. Okay, so you must understand that. So the water is actually come from middle point here, and then it will go to the radial direction. So means that water will go out at this area. So if you want to see the 3D pictures, so this is the impeller, okay, and then the water will comes out at this hole. So means that the velocity is like this, okay. The idea of Q equal A times V. So the V here is this velocity. So and then the A here is actually the cross-sectional area. So for this impeller, we found that the cross-sectional area is actually the gap between these two shrouds. So this plate is called shroud. So the gap between this one is actually the area, the cross-sectional area. So how to calculate this area is by calculating the circumference, the perimeter here, and then we times with the blade, with the width of blade here. Okay, so that's why the equation will become pi d. So pi d is the perimeter, and the b here is the width of blade. Okay, so that is the idea of this equation. So I hope you could understand this one. Okay, so and then if we see these two image, these two picture, okay, you will find that for the first picture, so the shape blade here, the shape of blade here is very sharp. So it will create a very thin area here, a very thin thickness of blade at the outlet here. However, if you see this picture, if your blade has area like this one, so it will create a thick area at the outlet here. Okay, so I hope you could understand, you could imagine this one. So what is the difference between this one and this one? So for this one, okay, for this situation where the thickness is very thin here, so we found that the water assumed can be passed through all this area, because this is a very thin gap. So we assume that this area is the cross-sectional area. So means that the calculation is enough, it's true by having the perimeter here multiply with the width of blade. That's why we could get pi d and b. Okay, however, if our blade here thick at the end here, so it will create a gap here. So means that the water, the liquid only could travel at this area only. Okay, let's say. So means that the water only could travel at this area. So means not all the area is the water will comes out. Okay, water only comes out at this area only. So means that the calculation of pi d times b is not correct anymore, because we have area that do not include in the calculation. So what we need to do is we need to add the area coefficient K here. So that's why in textbooks, they will write down the equation for VF. So it can be used for VF1 and VF2. Okay, so the official equation to calculate the value of VF is Q over K pi dB, where the value of K here is the area coefficient. So the area coefficient is actually reflect, okay, how many percent the area that you need to neglect from your calculation. So it's depend on the question. So you need to read question very well and try to imagine what happened to the pump. Okay, for example, if you have a statement like this one, if the thickness of the outlet blade is 50% from the total outlet area, so means that the white area here is actually 50% from the total area. So the area coefficient is 0.85. So means only 85% of the total area here can be flow, but water can go through only 85% of area. So please make sure that you understand the idea of K pi dB. If the situation is like this, okay, you could write VF2 is equal Q over K pi D2B2. But at this situation, you could say that the value of K is equal to 1. Because 100% area here can be through or by water. So meaning water can go through all the area. Okay, so I hope you could understand. There are two types of blade here. So one with thin thickness and another one with the thick thickness here. So the difference is if you have a thick thickness at the outlet and also thick thickness at the inlet, please make sure that you could you need to use this equation, and then you need to determine the value of K. So however, the value of K sometimes depend on the way, depends on the question. You need to read the question and you need to read carefully. Okay, so this is what I said. If the area here is very thin, so you still need to use this equation. However, the value of K here can be determined as 1. So mean 100% area of this one can be through by water.